Happy Friday, Year 9, and welcome back to another YouTube video with Mr. Crouch. Now, this is going to be your last YouTube video for week 9, and probably the last YouTube video for the rest of this term because, luckily we're going back to school next week, so that's going to be very exciting, even though we've still got some restrictions. It's going to be really awesome to see all of your happy faces once again. So, this lesson here is going to be the second part on our earthquake series. There was going to be another part next week, but you have to stay tuned with your own teachers to learn about that. But this is going to be earthquakes part 2. So before we start the lesson, make sure you're going ahead and downloading the worksheet so you can work along with this lesson. Alternatively, you can just download the worksheet and have a crack at it on your own. There is lots of information on there for you to go through, so it'll make it a little bit easier to work through it on this video. So, a little bit of a revision, so reminding ourselves of the last earthquake video. So there's 4 main layers of the earth. So we've got the crust, which is the outermost layer. It's between 5 to 50 kilometers thick and it's solid. We've got the mantle, which is the thickest layer. It's about 2,900 kilometers thick and it's made of like a semi-solid molten rock, so pretty much sort of solid. We've got the outer core, which is the 3rd layer. So it's about 2,300 kilometers thick. It's made of molten liquid iron and nickel, and it's responsible for Earth's magnetic field. And then we've got our inner core, which is about 6,000 degrees Celsius, and it's nice, hot, and solid. Now, when it comes to earthquakes, they usually come about from the result of faults. Now, there's 3 main types of faults. So we've got the strike-slip fault, which is what we tend to see at transform plate boundaries. We've got a normal fault. And we've also got a thrust or a reverse fault. Now, when we look at an earthquake, there's going to be 3 main features, and you can see them on the image on the right. So we start off with the focus. That's the starting point of the earthquake. That's where all that energy is being released from. We have the epicenter, which is the location on the surface of the crust directly above the focus. And then we've also got the seismic waves. Now, this is the energy that's being released from that focal point that's being pushed into the rock or into the mantle or into the liquid outer core and being transferred around the earth. And when it comes to seismic waves, there are 2 types of seismic waves when an earthquake releases its energy. So we start off with our P waves. These are called longitudinal waves. Or we've got S waves, which are transverse waves. Now, these waves have different properties that allow scientists to detect the origin of an earthquake. So, during this lesson, you guys are going to learn about the different types of seismic waves that an earthquake produces, and we're going to investigate this phenomena with a bit of an experiment. So, to be able to succeed in this lesson, you guys need to be able to describe the different types of seismic waves produced from an earthquake, and you need to investigate them through an at-home experiment, which we'll cover at the end of this lesson. So, seismic waves, we just talked about it before. There's 2 main types, and we'll start off with the first type, which is called a P wave. Now, a P wave, also known as a primary wave or a longitudinal wave, these are the kind of waves that are the first ones to arrive immediately after an earthquake happens at its focus point. So as soon as that earthquake happens, as soon as that energy is released, your P wave is going to be the first one that's going to reach the surface of the earth. Now, they have what's called a push-pull effect. So essentially, if you think of a building, it's going to push that building up and down. All right, not going to push it side to side, it's just going to push it up and down. And you can see that there's going to be compressions in those waves. So if you look at the image on the right-hand side, you can see that, yes, the fence is knocked over, but you can see the black lines going down into the earth, how some of them are really close together and some of them are further apart. That's showing evidence of that push-pull effect. Now, if you had a look at the videos that we put up on Tuesday about earthquakes, you would have noticed that we put up a couple of videos about slinkies. Think of it in terms of a slinky, all right? So when you have a slinky that's extended out and you push along it, at times there's going to be parts of the slinky that are nice and compressed, and other times the slinky is going to be nice and stretched out. Now, the second type of wave that earthquakes produce are called S waves. Now, these are also called secondary or transverse waves, and they're the second waves to arrive after an earthquake hits. Now, these are the more destructive of the 2. So the P waves are just the initial ones that give you some tremors, but it's the S waves that are the ones that are more destructive. The reason for that is that they have a side-to-side shaking effect that causes structures to shake. So rather than just pushing them up and down, it's going to push them side to side. So if you've ever thought about playing Jenga, if you bump under the table, it's just going to push your Jenga blocks up into the air, but they're not necessarily going to fall over. But if you shake that table side to side, there's a very big chance that those Jenga blocks are all going to fall down. And you can see evidence of that on the right-hand side in the image, and you can see that the ground is all wavy and shaky. So what's the difference between these two? So P waves are faster than S waves, so that's why they get there first. They tend to go between 1 and 14 kilometers per second, so not per hour, we're talking per second, which is pretty insane if you think about it. So yeah, the P waves are going to get there first, and then the S waves are going to get there second. Now, they have the different effects. So the P waves are going to give you that push-pull, so they're going to push structures up and down, as opposed to S waves, which are going to push them side to side and be a lot more destructive. And the most important difference between these two is that they can actually travel in different mediums, so like solids, liquids, and gases. So you might be sitting there and thinking, hey, like, Mr. Crouch, what's the medium? And no, it's not a psychic. I thought that at first when I looked it up, and that's all the internet would tell me about. But that's okay. So what is a medium? So a medium is a substance or a material that can carry a wave. So when we think about, for example, sound, all right, so sound is a form of waves, and you would have learnt about this in year 7 or year 8. So if you speak, the reason that you can hear sound or hear voices or hear noises is because those sound waves that you're producing are traveling in the air, right? So those air molecules are vibrating, and it's allowing that sound to travel. That's why they say that notion, or there's that idiom that you say that no one can hear you scream in space. The reason for that is that there's no medium for that sound to travel in. So obviously you can't breathe in space to begin with, but if you try to yell in space, no one's going to be able to hear you because there's no way for that sound to travel. Now, when it comes to seismic waves, P waves and S waves can only travel in certain mediums. Now, we touched on this earlier in the revision section, where we talked about scientists being able to pinpoint earthquakes by looking at the types of waves that are produced. So P waves are able to travel in solids and liquids, and S waves are able to travel in solids only. Now, if we have a look at the next slide, what we're going to show you is an example. It's a transection of the Earth. So we've cut the Earth in half, and we're able to see all of the layers of the Earth. Now, obviously, this isn't a real Earth. That's just an image. But we'll be able to see the difference in the S waves and the P waves. So firstly, we'll look at the P waves. So we can see at the top that there's an epicenter, the epicenter being the place on the crust of the Earth where the earthquake is directly above the focus point. So the focus point being where that energy is coming from. And all of these lines, all of these black dotted lines and the red dotted lines are those P waves that are being released from that focus. Now, what you can see is that the black circle on the outside, that's going to be our crust layer. The green layer is going to be our semi-solid mantle. The light or the darker of the blues, that's going to be our outer core, which is a liquid. And then you've got the lighter blue, so the sky blue in the middle, which is going to be our core, which is solid. So as you can see, the P waves here are able to travel through the entire Earth. The reason being, the entire Earth is either made of a solid or a liquid. Right? Now, you can notice as well that there's a P wave shadow zone. That's not important for you guys to learn about, but what's important for you guys to know is that those P waves are being released from that earthquake, and they are getting to the other side of the Earth or to different places in the Earth. So have a think about why that might be important. Now let's have a look at the S waves. Now, S waves, as you can see here, there's a bit of a difference to what the P waves are. So when we look at the mantle, so the green section, you can see that the S waves are nice and normal, right? They're able to travel through, but then you can see at the bottom that there's this really big S wave shadow zone. Now, again, the shadow zone isn't too important for you guys, but what that's telling us is that those S waves aren't able to get through the outer core, so the darker blue section. The reason being, the outer core is liquid. So P waves are able to travel in solids and liquids, but S waves, so that's the really destructive ones, they're only able to travel in solids. So why might this information be helpful for scientists? Have a think about that in your own time, and we'll discuss that next week when we talk about risk management for earthquakes. But definitely have a think about why knowing where, or like why we can look at these patterns here and these trends and go, okay, where we can use this information. So what you guys are going to do now is a bit of a first-hand investigation to look at S and P waves. So what you guys will need to do is, to start off with, you need to watch the video on how to make a paper slinky. Now, I've uploaded 2 videos into the Google Classroom, so you can either make a keychain paper slinky or you can just make a regular paper slinky. The regular ones are going to be quicker to make, but if you guys had a crack at it the other day and had a crack at the keychain slinky, then you can definitely use that as well. All right, what you need to then do is go ahead and make your own paper slinky so that we can use this. If you do have a slinky at home, feel free to use that as well. But it's always fun to, make your own things. What you then need to do is you need to have a look at the Seismic Slinky worksheet and have a look at step 1 and 2. Now, you guys aren't going to work on this worksheet. You'll work on your main worksheet and answer all your questions on that. But the Seismic Slinky sheet will have all the information as to what you need to do with this experiment. So we're only doing step 1 and step 2. Step 3 and onwards, they aren't important for you guys just yet, but we're just going to look at step 1 and step 2. Once you've done that, have a look at your worksheet. All right, so the lesson 10 worksheet on earthquakes part 2, and have a crack at the worksheet questions on there. So that'll have all the questions and the copy and complete ones from earlier in this lesson, as well as the questions from your practical. So once you've finished watching this video, if you haven't already, go ahead and download that worksheet and finish off the worksheet and the practical experiment in the Year 9 Google Classroom. Submit your worksheet to your individual Google Classroom under your attendance once you've done all of that. And then once you've finished all of that, have a crack at looking at the top 10 earthquakes of all time in preparation for next week. Now, reminding you guys that next week we're going to be going back to face-to-face lessons. So this will be the last YouTube video from me. But thank you very much for coming along with this little journey of mine. I hope you've enjoyed these YouTube videos, and I'm looking forward to reading your results from these experiments. So good luck, Year 9.